Nope. This is, we're going to talk for a second about antiderivatives and why is it always plus c. One of my favorite odd functions, guys, one of my favorite odd functions is y equals x cubed. All right? We can understand that. That makes sense to everybody, right? And the derivative of that function is easy. Do we agree? The derivative of that function is y equals 3x squared. Y prime is 3x squared. It's an easy derivative. We can easily see that's an odd function, so the derivative is on both sides. It's increasing the whole way. So I'm going to put this on infinite clone. Because if I slide up the exact same one, all right, and I move this all down the page a little bit, all right, all right, move this menu out of the line. If I slide this down, here's what I want you guys to notice. The derivative here, right, at some point is exactly the same as the derivative here. When I shift this up some distance, which I'm going to call c, it simply doesn't change the value of the derivative. It's 0 here. What is it here? 0. It's, positive 2 here. What is it here? Positive 2. As long as the x coordinates are the same. It just doesn't matter. So when we have this derivative, right, which is the same derivative for both the red curves on the board, we don't know where in space it is set up. So when I take the antiderivative of y prime equals 3x squared, I add 1 and divide, and we know it's x cubed, but I always do the same system. I always leave the coefficient, guys, and I always divide by the new coefficient, and then I simplify. But every time we do this, we never know where it is unless we have an initial condition to help us. Maybe it says it's through the origin, so you know c is 0. Maybe it tells you that the y-intercept is 1, so you know c is 1. Point is, you have to find a way. But right now, this is the general form antiderivative, all right? General form, because every time we do this, shifting a function up and down never changes the rate of change. Okay? So let's try another one here. So let's use our plus c knowledge now and actually take a derivative and make a function. So I give you f prime equals x times the square root of x. So f prime equals x times square root of x, and f of 1 is equal to 2. All right. We want to do the antiderivative. So I gave the initial condition, so we're going to go plus c, but then we're going to solve for c here. Okay. And that said, we got to be careful and watch for algebra tricks. There's an algebra trick right here. I definitely do not want 2 terms. I want 1 term. So if you want to pause me and try, go ahead. Otherwise, I'm going to show you the first step. I think this, guys, is a mandatory first step. I don't know if I can solve it the other way without this step. All right? And now the antiderivative is really easy. Add 1, right, to the coefficient and divide by the coefficient. We're going to add, so I'm going to get f of x is x to the 5/2 divided by 5/2 plus c.
So why is it divided by?
Why is it divided by the coefficient? Because, yep, and now when I flip it up, you see it now, Sam? If I flip it up, it becomes 2/5.
2/5, yeah.
Now, I also know I have an initial condition here. So instead of leaving c, I could put in 2 and 1. I like 1 because 1 to any power is 1. I solve for c by subtracting 2/5. I find the c. So guys, this time, because I was given the initial condition, I can write this as 2x to the 5/2. Yep. plus 1 3/5, which I'll probably write as 8/5. I would probably write it improper, but either way, and that is the antiderivative of this function, or this derivative up here, at this initial condition. If I change the initial condition, this value right here will change, okay? All right. So everybody, do we agree a polynomial, this is not too bad of an antiderivative. We want it, but you can't jump from f prime to f. So,
Is there any like application for
yes.
taking the antiderivative, I guess we say, the original? Is that even something? You did like 2 steps to get to the original function. If you like did it another time, is that even like? You know what I'm saying?
Yeah.
Go past the original function. Is there even like any?
So let me finish this. All right, so everybody, did you get this first derivative? You have to have a c every time. So here's c1, which gives you the instinct that there's going to be c2, right? Now we integrate this. And I know that this is an easy derivative. I picked one where it's not too hard. All the coefficients really are not that hard to calculate. But here's the big part, guys. You integrate c1, it becomes c1x, right? And you integrate, if you have another derivative, you have to have another constant. So my function in this case, starting from the second derivative, is going to be this. X to the fourth plus x to the third minus 2x squared plus c1x plus some c2. So if I was going to solve for c1 and c2, what would I have to have?
Oh, so the X.
Yeah, because you integrated c1, it becomes c1x, just like you integrate the 4. If you're going to get rid of, yeah, if you're going to do this problem, you need 2, guys, 2 initial conditions. And in the book, this problem had this condition. F of 0 is 4. F of 1 is 1.
Oh, that makes sense.
So then you can get rid of the c. Well, no, you got to carry the c's all the way to the bottom because they're both initial conditions of the function.
But
So you
that
have
would
to.
be a number.
Yep. So now, everybody, we see that since the y-intercept is 4, c2 is 4, obviously, right? Because you plug 0 in for x. So then I can just plug in the second one. F of 1 equals 1, so 1 plus 1 minus 2 plus c1 plus 4. Looks like c1 is -3, guys.
Why is the C2 4?
Okay, the initial condition is f0 equals 4. So 0, right? You plug in 0 for x,
Oh.
and the result is 4.
Okay, got it.
Yep, I'll write it out now. So they get C2. So C2 had to be 4. I kind of skipped that green one.
Yeah. Oh.
No, that's fine. And that's when you get, John, please ask. So here we go. And so, guys, C1 is -3. And again, if you're going to do this on the AP, on a test, and I said find the condition, you have to take one more step and write the whole thing out, right? With the proper numbers. All right? And that is the function for the 2 blue initial conditions I gave. Every time you step up an antiderivative, there has to be a constant. And every time you take the antiderivative of a constant, it gets an x term. This is the hard part, usually, initially, for us to not forget to put the C1, get C1x, and to get the C2. All right?